Hi, in this video, I'll go through convolution of series, also known as the product of series. And so, let's say we have two series of terms pertaining to an and terms pertaining to bn. Then cn equals to the summation from 0 to n of ak bn minus k, and that's really what is known as a convolution of series. So the terms from an are multiplied to bn minus k, and then you sum from k from 0 to n, and that's your definition of cn. And so the sum of cn is known as the product of the two given series. So what's important to note is that cn itself is a summation. So there's the limit of cn is the limit of this partial sums, and that the sum of cn is also a series, and so it acts like a double summation. And so one thing to take note is that if both the series an and bn converges absolutely, so it's important absolutely is here, then cn will converge absolutely, and the summation cn, the series cn, it will also converge absolutely, and that the series cn will equal to the series of an times the series of bn. And that's why it's known as the product of two given series. And so the proof follows because we consider the following result. So you take a summation of all the n from all the positive integers, and then you take another sum from 0 to n. Then ak, you consider the absolute value of ak times bn minus k. And then you can rearrange the terms, and you can just think of it as a lattice grid. So now your indexes run through integers cross integers. Then because k and l aren't related, you can split them up into the double sum again. And then this part is only in terms of k index, and this part is only in terms of l index. And so you can take the sum of ak times the sum of bl. And because you know ak and bl converges absolutely, this part is less than infinity, and this part is also less than infinity. And so the whole term will be less than infinity. And should you think we can just sum across all the integers instead of restricting ourselves? Is because if there's any integer that these two aren't defined, then it's treated as 0 basically. So you don't really need to care about it. So you can just take over the sum of integers to make it the proof. It shortens the proof and tidies it up instead of making it very messy. And so because the whole summation is less than infinity, every term here must be less than infinity as well, and it goes to 0. And so this means that this term converges, and this term is basically just saying that cn converges absolutely. And because cn converges absolutely, the summation of the modulus cn will converge, and this shows that the series converges absolutely as well. And then the product will really be this series an times series bn products. And so this proves the proposition that if you know that an and bn converges absolutely, then the convolution will converge absolutely. But if you just take a random sequence that you do not know whether it converges absolutely, then you can't be sure that cn equals to an times bn. And you can just consider this series over here, 1 minus 1 over square root 2 plus all the way, and you form its product with itself. You can prove out like Rudin, so you just follow what he's shown. Then in the end, Cn will not converge to 0, and hence the summation is not satisfied. So, and that's really because this series over here does not converge absolutely, because it's the P series where P is less than 1. And so what we shall note is that if we do not know that AN and BN converges absolutely, it tells us nothing about CN for now. But if we do know that AN and BN converges absolutely, then CN will converge. But while we shall not prove the next theorem, we shall state it, and the proof is really more of an algebraic exercise where you just need to be clear about what notations you are using, and you can just read the proof in Rudin or online. But these two theorems are important in stating when a convolution converges. And really, this theorem by Martins says that if you know one of the series converges absolutely, say to A, and you know and the other series just converges to B for some but it may not be absolutely, but just sequentially, then you know Cn being the convolution, the series Cn will converge to A times B. So as long as one of the series converges absolutely, then it's enough to show that Cn converges. And if it doesn't, then you have this example to show that it might diverge. And the proof really won't be go through in this simple tutorial video, but you can really read the proof in Rudin textbook. But it's really a notation that you need. It's all the notations that you need to keep track of, all the indexing. That is the hard part, but the proof should be easy to follow, because it's really about bounding it to be less than infinity. And so this theorem by Martins is useful because now you don't need the absolute convergence of two series, but only one. And the next theorem is by Riemann, and it says that if you know that a series is not absolutely convergent, then you can pick any two numbers in between infinity to minus infinity, and you can then rearrange your terms in the sequence such that the partial sums has a lim_inf of alpha and a lim_sup of beta. And if alpha is strictly less than beta, then this new rearranged series does not converge. And then if alpha equals to beta, then we can say that this series converges to the new value we want. And so this is a very interesting theorem because it shows that for any series that doesn't converge absolutely, you can rearrange its terms so that you can create any partial sum that you want. And again, we won't prove this because the proof of it is a very standard way, but you just need to take note of all the indexing to get to where you want to prove. And so I'll leave it to you to read it in the textbook, but you can really take note of this theorem that says that without absolute convergence, then the series converges to any value you want under a rearrangement. And so we like to take note of what is a convolution because it's useful for us, and we'll see why in the next video. So this is all for this video, and I'll catch you in the next one. Bye.